Hello, welcome to Common Core Algebra 2. Today we're going to be learning about function notation. All of our function definitions today will be given to us as an equation in function notation. Function notation merely means that the left side of the equation has some kind of a designation that it is a function. So it might say f of x, it might say g of x. Any letter can be used for our function. For our first equation, the function is f of x equals 5x minus 2. This merely tells us the rule that we are going to use for any input value x to find the output value for the function. So for example, in the first equation, f of x equals 5x minus 2, if our input value is x equals 3, that means we are just going to substitute 3 in for x. So we are going to say 5 multiplied by 3 minus 2. Now, of course, we can do that calculation. 15 minus 2 is giving me an answer of 13. The output value when x equals 3 would be 13. Let's go to the next example, f of negative 4. All that changes here is our input value. So to find f of negative 4, we are going to substitute negative 4 in for x. So 5 multiplied by negative 4 minus 2 is giving us an answer of negative 22. So we read that as the function value at negative 4 is equal to negative 22. That tells us that the input was negative 4 and the output was negative 22. Now, function equations can take any form. You'll see the next example is a quadratic equation. G of x is equal to x squared plus 4. We could just as easily be putting these numbers, the inputs, into our calculator and storing them as x values. I'm going to show the calculations each time today, but you can experiment with using your calculator as well. So for this one, we're going to say 3 squared plus 4. So our x value is being squared, and then we're adding on 4. Of course, this answer gives me 13. So that tells me when my input is 3, the output is 13. Trying negative 1, be very careful with that negative sign. So I'm going to put parentheses around the negative 1, and I'm going to square that input. And then I'm going to add 4. Negative 1 squared, of course, is positive 1. Positive 1 plus 4 is equal to 5. So that tells me that when my input is negative 1, my output is equal to 5. You'll notice that I put a graphic off to the side here showing a function machine. This is how you might want to think about function notation. We have an input x that goes into the machine, and the machine does some kind of rule to that x. And out pops the output, which is just our f of x answer. We need to make a change in our notes here today. I apologize for this, but it should have said, for example, C, h of x. So if you could change that g to an h of x equals 2 to the x power, you'll see that we've got an input of 3. So we're going to put 3 in for x, so 2 to the third power. 2 to the third power, of course, means multiply 2 by itself 3 times, so 2 times 2 times 2, which gives me an answer of 8. So my input is 3, my output is 8. Now, be very careful when you've got a negative number being put into an exponent. This would, of course, mean 2 to the negative 2 power. Let's recall back from Algebra 1 that when I have a negative exponent, that means take the reciprocal of the base. So this is the same thing as 1 over 2 to the second power. You could take a second to test that on your calculator as well and see if you get the same result. 1 over 2 to the second power, of course, is 1 over 4. If you put 2 to the negative 2 into your calculator, you're probably going to get a result of 0.25. But of course, if you convert that over to a fraction, that is 1/4. So that tells me that when my input was negative 2, my output was equal to 1/4. This is just another way of writing equations, but as we get into more sophisticated math and Algebra 2, function notation is going to be much more popular. So let's recap here just the notation that we're using. The output usually is our y. Another way of writing y is f of x. This gives us a way in equation notation to write both our input, which of course is our x value, and also taking a look at our rule, which is going to be either f or g or h, to get our output, which of course becomes our ordered pair x comma y, where x is of course the input and y is the output. So an equivalent way of writing this would be x comma f of x. So where we see f of x, we can just think y. Now we're going to be examining function rules in 3 different forms in this course. In the first example, you saw that we had function notation given to us as an equation. That's going to be a very popular way to write equations in function notation. And we'll see that throughout our course and through the next courses that you'll be taking, pre-calculus and calculus. We'll also be able to see function rules given to us as ordered pairs on graphs. So we can read values from graphs and know what the input and output are. Likewise, we can use a table of values. When we look at a table of values, the independent variable generally comes first, and that's my input. The dependent variable comes second, and that's my output. So let's take a look at an example of one of those problems using a table of values would be what we see in exercise number 2. Boiling water at 212 degrees Fahrenheit is left in a room that is at 65 degrees Fahrenheit, and it of course begins to cool. When something is warmer in a cooler environment, it tends to cool down to get close to the temperature of its environment. Temperature readings are taken each hour and are recorded below. The temperature T is a function of hours H. We're going to see later in the course that this application is actually called Newton's law of cooling. Some of you may see that also in chemistry or possibly physics. But we're going to be having lots of examples of Newton's law of cooling when we get into our exponential chapter. For today, we just want to look at this table of values and use the table of values to talk about inputs and outputs. So just familiarize yourself with the table. We see that the first line represents hours. Now the hours are going to be how many hours the water was left in the room. So the 0 would of course stand for we just stopped boiling the water and set it on the counter in the room. 1 would represent 1 hour after we left it, 2 hours, 3 hours, all the way up to 8 hours. And you'll see that at 8 hours, we are close to that. We are actually at that value of room temperature, which was 65. It's not possible unless we add another characteristic like ice for that temperature to go below the room temperature. Now the T of H column, actually I guess it's a row this time, is our dependent variable. Our temperature is going to depend on how long we've left the water sitting out on the counter. So when we first take it off the stove, we see that it's at its boiling temperature of 212 degrees. So after 1 hour, the temperature is 141 degrees. After 2 hours, it's 104 degrees. And that's actually the first question that we want to answer. We want to find T of 2. Well, T of 2 just means what's the temperature, what is the output at time 2. So for us, T of 2, according to this table, is equal to 104. Now, since this does have a unit, we're going to write it as 104 degrees Fahrenheit. Now, let's move on to the second half of part A. Now we want to look at T of 6. T of 6 just means what's the output when the time is 6. So what is the temperature at time 6? So we look at that value according to our table, and we see that T of 6 is equal to 68. And again, let's put the unit on that, 68 degrees Fahrenheit. So we can get some very valuable information just by looking at our table. We don't have an equation this time that tells us how to evaluate the function. Instead, we just have a limited number of values, input values along with their output values. At certain times, what is the temperature? Now, the next part of the question says, well, for what value of h is T of h equal to 76? Notice that now I'm being given the output value. That means I want to know what's the time when the temperature is 76 degrees. And you'll notice that we see that right in our table. There's 76 degrees. How many hours did it take? It took 4 hours for the water to go down to 76 degrees. So our answer for this is that the input is 4 hours when the output is 76. But just take a look at that and see how the question is asked in kind of a backwards format, kind of like a Jeopardy way. I'm given the answer. I want to know, what was the question? What was the input? Taking a look at part C, now we're given a value that's actually not even on our table. We want to say, oh, I wonder when the temperature could have been 100 degrees. Given the fact that these temperatures keep going down and have to go through every single temperature in between 212 and 65. This is called a continuous function. All values are covered. Well, we want to know, when could the temperature have been 100 degrees? When I look at my table, I say, oh, well, it was 104 degrees at 2 hours, but then it was all the way down to 85 degrees at 3 hours. So it had to be sometime between 2 hours and 3 hours when the water was 100 degrees. Now, we're never going to say, oh, it was exactly 2.5 hours, because we don't know right now, according to this table, exactly when between 2 and 3 hours it was. Instead, we'll just be able to ballpark it and say, okay, I know it had to happen between 2 hours and 3 hours. Here's an example of a graph, and using a graph to find function values. So looking at this graph, you'll notice that we have our x variable, of course, along the horizontal axis, the y variable, or the output, along the vertical axis. And every ordered pair on here can be written, every point on here can be written as an ordered pair, x comma y, where x is the input and y is the output. So if we want to use this graph to evaluate function values, I'm going to specifically look at f of negative 1. So to find f of negative 1, I'm going to go over to my graph, and I'm going to locate where negative 1 is as an input. And I see on my graph that here's the point where the x-coordinate is negative 1. If I write that as an ordered pair, then I see that my ordered pair is negative 1 comma 0. So if I'm asked for the function value at negative 1, I'm going to give as my answer the y-coordinate, the 0 answer. So 0 is my output when my input is negative 1. Likewise, I'm going to go to the x-coordinate of 1, and I see that where x is 1, the function value is way up there. I have to be on the graph. So if I count out the values, I see that my ordered pair would be the ordered pair 1 comma 4, according to the graph. So therefore, the function value is equal to 4. Hopefully this is a pretty easy application for you, because we're just looking at the graph and finding the y-coordinate at the given x value. For the third one, I'm looking for the function value at 5. So let's count over. I've got 1, 2, 3, 4. Here's my 5, according to my x value. If I go down to that ordered pair, The ordered pair would be 5, negative 4. So therefore the output value would be negative 4 when x is equal to 5. For part B, we want to look at f of 0. So to find f of 0, I'm going to go to my graph, and 0 just means I'm along the y-axis. So here's the point right here. When x is 0, it looks like f of 0 is equal to 3. Now think for a minute what that point would have been called. I'm sure you saw this back in algebra and also in geometry. This point should be called the y-intercept. So the y-intercept is the place where the x, or the input value, is 0. It's the place where my graph crosses the y-axis. Now notice that for part C, we're asked the question in a different order. We want to know, when does the equation f of x equal 0? So for this one, we know that we want the output to equal 0. The output, of course, is our y coordinate. So we want to know, where does the y value equal 0? So this time we're being asked for the x value. Oh, it could possibly be more than one value, where the output was 0. You'll notice that in part A, we already saw an example of one of those places, where x is equal to negative 1. According to my graph, let's focus on that point again right here. That's the spot where the y is 0. Now, is that the only spot? I don't think so. I think there are some other points where the y is 0, so I'm going to go find those on the graph and circle them in red. So I see that at this spot right here, my ordered pair would have a y coordinate of 0. What's the ordered pair there? It would be 3, 0. So that tells me that another place where the f of x is equal to 0 is when x is equal to 3. And there is a third spot. Let's look at that spot right here. If I count over, that's looking like I might have the number 7. So my third place where the output is 0 would be at x equals 7. Now I'm going to take a second to erase all the notation on my graph because we want to focus on something else for part D. So give me a minute to erase this part. No, maybe not. Let's take a look at the equation f of x equals 3. So f of x equals 3 is the same equation as y equals 3. So I'm going to graph on here the horizontal line y equals 3. Now I see that I already found one spot where y was equal to 3. That happened at 0, 3. Now there does seem to be another spot right here. That would be at 2, 3. So there's another spot where the output is 3. But I see that there's actually a third spot on my graph where the y coordinate is equal to 3. But this one's not as easy to read from the graph. So this question says, between what two consecutive integers does it lie? Well, if I count over on my x-axis, I see that it has to happen between the numbers 7 and 8. So it's happening at a spot where the x-coordinate is between 7 and 8. Right now we're not going to know exactly what value, but I know that it's between 7 and 8. So this is the answer that we're going to get because our question asked for the largest solution. So that would be the one furthest to the right. For our last example today, I want you to get out your graphing calculator, and we're going to enter this equation into our graphing calculator. Now don't be intimidated by the fact that the equation is given in terms of h for the function name and t for the input variable. So here is the equation that I'm looking at right here. H of t is equal to 50 minus 16t squared. If you could pause the video for a minute and enter in your calculator under y1 the equation 50 minus 16. We're not going to use the variable t, we're still going to use x because our calculator understands x instead of t. We'll just know to convert it over to t's for this particular application problem. So you're going to enter 50 minus 16 x squared. Then I'd like you to make a table of values on your calculator, and when you come back we'll talk about how we're going to set up that table of values when we write it down. Hi, welcome back. I hope you put your equation into your calculator and found a table of values. Now, when you take a look at your table of values, you'll notice that it says we want to determine to the nearest tenth of a second. So that means that when I'm on my graphing calculator, I don't want to be counting by ones on my table. So I'm going to go back to the part of my calculator that is second, table set. That's the second key over on the top line. So I'm pressing the second key, and then I'm pressing the table set. I'm going to change the delta table on my calculator, and I want to make the delta table equal to 0.1 so that I can count by 0.1s on my table of values. I'm going to make my table start be 0. So start value of 0. I know I wrote those in the opposite order that it's going to show up on your calculator. So you want the first line to say 0 and the second line to say 0.1. Now when we do that, I actually see that between 0 and 1, the ball doesn't hit the ground. Hitting the ground would of course mean that my output must be a height of 0. And I see that it doesn't happen between 0 and 1. So I want to scroll down on my calculator on the table of values, and I want to make a table where I am specifically looking above the number 1. Now I'm going to start by putting the answer for 0 because we're going to have to make a graph of this, so I do want to know where the ball starts. So for this one, I'm starting with a height of 50 at time 0. Now I'm going to skip down to 1, and I know there are values in between there, but I'm going to go to 1 next. And I see on my table of values the answer is 34. I'm going to keep going by 0.1, so 1.1, 1.2, 1.3, 1.4. And I'm going to keep going until I see that the ball has hit the ground and see how long that takes. So at 1.1, the height is 30.64. I know there are other decimals there. I'm going to put just this. I'm going to go to the nearest hundredth, sorry. So 26.96 at 1.2. 1.3 would be 22.96. 1.4 is 18.64. 1.5 is 14. 1.6 is 9.04. 1.7 is 3.76. 1.8, all of a sudden my height is a negative value. I obviously can't go underground with this ball, so what really happens is it must hit the ground somewhere after 1.7. Now, because negative 1.84 is closer to 0 than 3.76 is, I'm going to estimate this to the nearest tenth at 1.8 seconds. I know that it doesn't take exactly 1.8 seconds because at 1.8 seconds I've got a negative height. And again, remember that the H stands for height. So the answer to this question would be 1.8 seconds to the nearest tenth. Now, before tomorrow, what I'd like you to do is set up a graph of this. And I'm going to lay out your axes for you to help you get started. I'm going to say that this is 0, this is my t-axis, and this is my h of t axis. We're just doing a sketch. You don't have to do it on graph paper. I see that I'm going to divide up my x-axis so that from 0 to 1 goes like this, and from 1 to 2 would be over here. Now I'm going to try to divide this into smaller increments. You might have better success in your notes. This is going to be 1.5, but I'm going to put all the intervals in between for 1.1, 1.2, 1.3, and 1.4. Then I'm going to make 1.6, 1.7, 1.8, and 1.9 so that I can have all of the heights from 0 up to 1.7 that I put on my table of values. Now it's going to be too hard to do these tiny little decimals on our graph, so instead I'm going to count by tens on my y-axis. Again, remember that our goal is just to make a sketch of this motion of the ball as it falls from a height of 50 feet. So by tomorrow, just finish off your sketch and bring that to class with you. We'll be talking about this example some more in class tomorrow. Thanks. Have a great night.